So this is the second video that I'm recording in this series that I'm doing to help explain the background for this new appraisal method that I've developed. And before I can really explain how it works and what I've done differently, what sort of new and novel for this method, we need to kind of back up and look at some of the things that are sort of baked in to how we've approached data analysis in general and the sales comparison approach in particular in developing opinions of value. And my first video, I put that out earlier this week, and I got a question from Louis Pittoni. And this is a fantastic question, so I'm going to share it with you. Okay, so he says, you use the words determine and deterministic frequently to describe traditional methods. Since this series bridges appraisal and data science, I wonder if it would be helpful if you explicitly defined what you mean by deterministic versus probabilistic in an early video. The word determine is tricky because of its double meaning. I personally distinguish between setting or dictating on the one hand and ascertaining or researching on the other. One implies controlling an outcome, the other indicates the speaker is investigating a question. Many appraisers use determine to mean the latter, while some in the public accuse appraisers of doing too much of the former. I agree. In many places, it seems you are referring to the statistical definition regarding fixed inputs and outputs, but at times I wonder if you were referring to research. Maybe you're picking up on how the word is a frustration to me. In any case, clarifying that distinction could help the uptight semantic people in the audience follow your argument better. So Lewis's question is really helpful, and it's helpful because it really points out that there are two different things going on. So the answer to his question is that I was using that word, those words in both senses, and I'll show you why I made this example to make it a little bit more clear how both of them are important and they actually overlap some of these concepts a little bit, especially in the appraisal world. So let's look at this graph and what I was trying to convey. So this graph is random data points. I actually just created a random set of data between 20 and 40 on both the X and Y axis. So I just put some data points in space randomly. And so what I want you to know is that that is the system. So when I say the system, these data points collectively form a system. And this system has a structure and meaning. And in this case, the structure and meaning is complete randomness. I actually used a random function to randomize these numbers. So as appraisers, we're not dealing with random systems, but we are dealing with systems that do have a structure in human behavior. There are buyers and sellers, they're reacting, interacting together in a market in the context of real estate. And so, so we're luckily not dealing with random systems, but we are needing to deal with the fact that there is a system, and how we analyze that system is important. And so there's two uses of the word, Lewis, that I used. And the first is in the sense of, yes, I am selecting something, I am determining something as the appraiser. So if we look at this set of data, I have determined that I wanted to draw a linear regression line through this data set. And so that is something that I have determined that I think would be helpful. So that has implications. In this case, it's not helpful at all. It's not going to give me any meaning or predictive ability whatsoever for this data set and how it's actually structured. But I have determined that I wanted to use it. And so that is an important element to think about when we are setting up an analysis and we're considering how we develop, particularly the sales comparison approach, and how we deal with these different variables. The second way that I mean this is a in terms of a mathematically determined system. So what we have here is a system, and while it's random, it can be mathematically determined that this is the linear trend line. The formula at the top of the graph here is the formula that is mathematically the formula that best describes that set of data. Now, a couple of things here to note in problems with deterministic systems is how I determine my model. So how I determine the type of line, it's going to have a huge impact on the outcome. So we can see what the outcome is right there. What if I did a polynomial 2 regression line? That's now what the regression line looks like. It's a completely different explanation based on the system based on the technique that I've applied to this system. Now it's a polynomial 2 regression line. The outcome is completely different. And so what I have determined, and the fact that there is a different way of calculating this system based on what I've determined, they're both mathematically correct. So we have this polynomial 2. This formula is mathematically the best polynomial 2 description of this data set. And this is the best linear description of this data set. They're both mathematically determined. But are they helpful? Not necessarily. And so let's think about that, because ultimately we have to keep in mind not just that we're trying to do the right math, but we're actually trying to understand the underlying system. So let's look again at this is the grid that I showed you in the last video. So when we're talking about site size adjustment, for instance, well, I'm determining an adjustment. And like I said last time, that deterministic framework in terms of I am selecting something impacts the other adjustments and the extent to which they can be supported because they're connected. In this case, they're connected through correlation. They could be connected more organically. But the other thing to notice is that if I am determining an adjustment for site size and I'm bringing it in, where am I bringing it in from? I'm bringing it in from a different system. Okay, if I'm not deriving it from the system, which it can't be because this is an underdetermined system that you're looking at, well, where am I getting that adjustment from? I'm bringing that in from somewhere else. So I'm determining that where I'm bringing it from is relevant. The analysis that was done is the right kind of analysis. And ultimately, I'm making some assumptions. And a big one is that the system I'm applying it to is equivalent to the system that I'm drawing it from. And that doesn't just mean that they're similar markets. What it means is that the composition of the data that describes that market is also the same. So in terms of correlation, which we've been talking about, does the system I'm drawing that adjustment from have the same structure of correlation as the system in which I'm applying it? If not, then I can't really apply that adjustment. I can't know that that is the right adjustment for this system because I'm really applying it in a different system than what it was derived from. And that has implications because however that adjustment was determined from the other system, I am bringing that into all the inherent, even the noise from the data, just the variability within the data. I'm bringing all that in, implicit in that $5 a square foot that I'm applying in this grid. So, Lewis, I hope that clears things up. that when I'm using deterministic, I want you to think of both ways um, that can impact the analysis that I'm doing, the conclusions that I'm drawing, and what actually I'm bringing in implicitly into my system. So if we think of this three sales here as a system that describes a market, then I need to know what am I bringing in to this system that maybe doesn't belong. So next time we're going to talk about really the math side of this a little bit more and talk about that mathematical determinate system aspect. And I want to really explore the idea that there may be no unique solutions to a problem. And if there's no unique solutions, but you're applying a technique with a unique solution, what's really happening? And so we're going to explore that one next.